Today's preparation is about bolted joint preload. So on the left we have a bolt going through a material. We call it a bolt because it's going through a nut. Screws are what thread into a part. Just a matter of how you use it. This portion here is called the shank, and here's the threaded portion. There are no threads up here. This bolt is finger tight. We have dropped the bolt through and turned the nut until it is, quote, finger tight. We haven't used a wrench and really put a lot of torque on it. So what's going to happen when we do take that wrench and torque it? Well, the nut is going to advance up the threads, but this material is in the way, right? But you know from practice that even once it touches the material, you can get a few turns in. So what happens when you do that? Two things are going to happen. The material itself, the material inside the joint between the underside, the head of the bolt, and the top side of the nut here, everything that's in between there, this sandwich, we call it the joint, or we call it the members. The members are going to compress. You can see from the shape here that it's exaggerated, but this is kind of what it would look like. There's been some material compression. It's represented by the symbol here, delta M. It started out at this level, and it's compressed to this level. So the material, the members have compressed. And the second thing that's happened is because the material has some stiffness, when it compresses, it pushes back on the bolt, and the bolt stretches. So here is the stretching of the bolt. You can see originally the end of the bolt was here. Now the end of the bolt is down here. We're representing that with a delta B for bolt. So the member has compressed, the bolt has stretched. And when you stretch the bolt, you develop a preload, F subscript I. Think I is for initial. So that is some amount of tension that's inside the bolt, some stress that's over the cross section, even before you apply an external load to this joint. Normally we're going to apply some sort of load that's going to tend to separate the joint. That's why we have put a bolt through it, because we don't want these two parts to move apart from each other. But even before you start trying to pull them apart, there is some initial tension in the bolt called the preload, and we give it the symbol F subscript I. So preload is the tension in the bolt you get when you tighten it. There are some advantages to that. It helps resist untightening of the bolt. Right? When you apply that preload, then there's this force that's pulling the nut up against the material. That causes there to be friction between the nut and the material, or that causes between the head of the bolt and the material for there to be some amount of friction. So the more preload there is, the more friction there's going to be that resists untightening. It also resists the separation of the joined components. So we've joined these two components, and if this were just finger tight, then you could pull on it, and when you pull on these material and you try to pull it apart, well, the bolt is going to stretch a little bit because it's a spring, and these two pieces are going to gap if the bolt is just finger tight. If you've preloaded it, then you've got a lot of pretension that is holding the joint together. So even if you pull on this thing, it's going to stretch the bolt a little bit more, but it's not going to gap yet because the material is compressed. It's squished together. You have to pull on it pretty hard in order to separate the joint. It also increases friction between the two components that you've joined. So there's going to be more friction at this interface. Now, why is that a good thing? Well, consider if you had some sort of shear load, right? If you've got a force pulling this to the left and some force pulling this one over to the right. Well, yes, the shank of the bolt can handle that. You don't want to put the threaded portion of the bolt in shear. This has less cross-sectional area down here, and there's also stress concentrations. So it's better to use the smooth, unthreaded portion of the bolt for that. But look, if you've got this friction between these two parts, maybe you never even put the bolt in shear. Maybe it's just friction between the members that can resist the shear load. And finally, it reduces amplitude stress from time-varying loads. So because the bolt is preloaded and the material is squished together, now whenever I apply an external load, a tensile load here, it's going to stretch the bolt a little bit more, but it's going to tend to decompress the material. When the material decompresses, that equal and opposite force that it applies on the bolt gets reduced. And that causes, effectively, the total tension in the bolt is not just the sum of the preload plus an external load, it is the preload plus a fraction of the external load that you apply. And that fraction can be like 0.1 or 0.2, and it depends on the relative stiffness of the bolt compared to the members, to this sandwich here. Now, why is that good? It turns out it has implications for fatigue, and we'll study those later. But the short of it is, when materials see time-varying loads, They see fluctuation between a high load and a lower load. The greater that change in load is, the sooner that the part will fail due to fatigue, that fracture that occurs, the same sort of thing that when you're bending a paper clip back and forth. So we'd prefer, for fatigue purposes, it'll be less likely to fail due to fatigue if you keep a constant tension on the bolt with very little fluctuation rather than having a little bit of tension in the bolt and large fluctuations in the load. Having the small fluctuations with a large preload is preferable. So disadvantages. What's wrong with preload? Just that it complicates analysis, really. Everything else mechanically is good, and that's why we do it. So we're going to put up with the more complicated analysis. The tension of the bolt is no longer just equal to the applied load. It becomes a little bit more intricate how you size a bolt for a given joint. You also have to calculate what the preload should be, how much you should torque it. You don't just look in a catalog and see, oh, this bolt can handle this much load and use it. It's not quite that simple. And so we're going to learn how to do that today. So here's the process of analyzing a bolted joint. First, you need to determine what your external load per bolt is. So I'm going to give an example today that is a pressurized cylinder, and it's got an end plate on it that's held together by many bolts. And so the pressure inside the cylinder is pushing on the end plate with some force. But then we've got several bolts, so we can assume that the load is divided up equally among the bolts, and we get the external load per bolt, P, that way. Now, it's not always that simple. Loads are not always going to be evenly distributed among all your bolts, so that's problem dependent, and I'm calling that the first step, to determine that external load per bolt, P. We've got a lot of P's and F's that are going to be showing up as variables, so that's why I'm emphasizing that we call the external load per bolt P. Next step is to determine the tension, the resultant bolt load in each bolt. F sub B is the total tension in the bolt. And it's the sum of F sub I, which is the preload, which is proportional to the torque that's applied to the bolt. And we're going to also talk about some recommended values for what that should be, or you might need to choose it based on your circumstances. It's the sum of that preload and PB, the additional tension in the bolt that's caused by P. So P is that total external load per bolt, but remember, not all of it ends up inside the bolt. The tension of the bolt is not just the sum of the preload plus the applied external load P. No, PB is, in general, much less than P. And this should be surprising if you haven't done this sort of analysis before. I was surprised anyways, and we'll see how that's the case. I've got some videos that go through the theory of why that's the case, so you can watch those separately. Today we're going to just use the equations that you can derive by considering the relative stiffnesses of the different components. So it depends on the joint stiffness, the bolt stiffness, and the members. Okay, so once we've determined the tension in the bolt, we are going to ensure that the tension, that force in the bolt, doesn't exceed the limits. And there are several limits that we need to consider. We don't want to exceed the proof load of the bolt. You've already been exposed to proof load. Sometimes we're going to call it yielding the bolt. That's the failure state, even though there's a difference between proof strength and yield strength. Sometimes we'll say that we don't want the bolt to yield, even though we mean we don't want it to exceed the proof load. The joint can gap. That's another thing, right? We said that if you just finger tight the bolt, and if you try to pull the joint apart, then as soon as you stretch the bolt, even just a tiny little bit, then there's going to be a gap in the joint. And let's say you were trying to hold a pressurized seal in that cylinder. Well, air is going to start leaking. You don't want that. So even with preload, you need to ensure that you have enough preload so that when you pull, there's not going to be any gap. And also you need to consider the fatigue strength of the bolt material. We haven't talked too much about fatigue, so we're not going to be doing this analysis here, but we'll learn these later. Today we're going to talk about the preload, how to figure out what the preload is, and how to calculate the total tension of the bolt, assuming you know the bolt stiffness and member stiffness. And next time we'll look at how to calculate what those are. So what I want you to get out of this module is that you should be able to determine the typical recommended preload for a bolt. When you're designing something, you might want to adjust this up or down, but here's some general recommendations. You'll also be able to calculate the torque that's required to produce that preload. So you get out your wrench and you don't just crank it down until it feels snug. You get out your torque wrench and torque it until the torque wrench clicks, or if you're using a dial sort of torque wrench, then until it reaches the recommended preload. And then, given the stiffness of the bolt and the joint material, we're not going to calculate those today, but if you have those, then you'll be able to compute the total tension in the bolt when you apply an external load. It's not just the sum of the preload plus the external load, it's the preload plus a fraction of the external load, a fraction that depends on the stiffness of the bolt and that joint material, the members. So remember that proof load is the tension that a bolt can withstand without acquiring a measurable permanent set. It's the smallest amount you can measure. And how is that different from yield? Well, it's the same concept as yield. Permanent set, that's what yield means. But when we define the yield strength of a material, we use the 0.2% offset method. The proof load of a bolt material, they measure much more carefully, and they say, all right, what's the smallest amount of permanent deformation we can measure? That's what we're going to call the proof load. So the proof load for a bolt is the proof strength of that material multiplied by the tensile stress area. And what's that tensile stress area? It's the area of a circle that has a diameter that's equal to the mean of the pitch diameter and the minor diameter. So you just use the average of the pitch diameter, dp, plus the minor diameter, dr, r for root. Take the average of those two diameters, so it's a little less than the pitch diameter, and you calculate the area of a circle with that diameter. That's your tensile stress area. Now, fortunately, we don't have to actually run through this calculation. That's just conceptually what it is. These are tabulated for bolts. And so is the proof strength for different bolt materials, for different SAE grades. We know what the proof strength of it is. We can look up for the bolt size and number of threads per inch. We can look up the tensile stress area, and we can calculate the proof load of the bolt. So what's the recommended preload? This is what it says in Shigley. For non-permanent connections, if you plan on reusing your fasteners, you're not supposed to reuse your bolts. You're supposed to toss those after you torque them once, but you can reuse the fasteners if you torque it up to 75% of the proof load of the bolt. If you have a permanent connection, you can go up to 90% of the proof load of the bolt. So you are almost yielding the bolt, and when I say yield, I mean exceeding the proof strength. You are almost yielding the bolt when you torque the bolt up to 90% of the proof strength. But don't worry, when you apply an external load, that doesn't mean you have got 10% of the capacity of the bolt left. Because of what we're saying with the relative stiffness of the members and the bolt, you take that into account, you only add a small fraction of that external load. So it turns out that this is still going to allow you to handle a lot of applied load, even if you preload it very high. It also defines what we said in the last slide, that the proof load of the bolt is the product of the tensile stress area and the proof strength of the material the bolt's made out of. And it also mentions that the proof strength is around 85% of the yield strength, so that's a good estimate. So let's do an example. What's the recommended preload for a permanently installed SAE grade 5 quarter 20 bolt? So it says permanently installed, so according to the last slide, we're going to want to go up to 90% of the proof load of the bolt. So we need to calculate the proof load of the bolt according to this formula here. So we are going to first look up the proof strength of the bolt material. It says it's SAE grade 5, and if you look in the appropriate table of the book, then you'll find for a quarter 20 bolt, the proof strength is 85 KSI. And then we can also look up a quarter 20 bolt, what its tensile stress area is. So we look that up for a quarter 20 bolt. If you had a fine threads, you'd look over here, but for a quarter 20, the tensile stress area is 0.0318 inches squared. So the proof load is just going to be the product of this and that. The proof load is the product of those two, 2,700 pounds. And so what is the preload? It's 90% of that for a permanently installed connection. Preload is 2,432 pounds. So when you apply torque to a nut or the head of the bolt, that's what causes the preload, because the nut advances up the threads, squishes the material, causes the bolt to stretch, and that causes the preload in the bolt. And here's the general equation, right, for the torque relationship between torque and force. We learned this in the context of power screws, but guess what? We don't have to use it. It simplifies down for standard fasteners because they follow a certain relationship between the diameter and the lead, and the collar in this case is going to be the friction between the head of the bolt, or usually the nut, and a washer. Turns out that it simplifies to something like this. The torque is just the preload we need multiplied by the major diameter of the fastener and some constant K. All of this stuff simplifies down to a constant K. So it's just an approximation, but it's a pretty good one. And Shigley gives table 815, might vary in your version of the book. For different bolt conditions, we've got different constants K. So if you've just got a black finish bolt, hasn't been plated, there's no special lubrication or anything, you might get a K that's as high as 0.3. It's going to take more torque to get a given preload. If it's zinc plated, then it takes less torque. If you lubricate it, even less. Now in some cases, figuring out what the preload is going to be or how much you need to torque it to get a given preload is not good enough. Sometimes you want to measure the preload directly inside the bolt, and there are some technologies for doing that, but they tend to be kind of expensive, and so this is often what we end up doing. So let's do an example calculation of what torque is required if you want to produce the recommended preload for a permanently installed galvanized SAE grade 5 quarter 20 bolts. So the same bolts as before. We already calculated the proof load on that, but now we know that it is galvanized, and galvanized means zinc plated. So we're going to use the K factor 0.2 that's in that table. And here's the calculation. The torque is that K times the preload, which we calculated before, times the diameter of 1/4 inch. So 0.2 coming from this, the 2,400 pounds that we calculated before as the preload, times the major diameter of 1/4 inch, and that's 122 inch-pounds force. So get out a wrench and torque it up to that value in order to get the recommended preload, which was 90% of its proof strength. So we said that once you calculate the preload, once you know the preload and the torque required to get it, you also would be interested in the total tension in the bolt, F subscript B. That is the sum of the preload and the additional tension in the bolt that's due to the external load. And that PB is not equal to the external load. It's a fraction of it. So let's do an example. The end cap of a 6-inch diameter, 2,000 psi pressure vessel is secured with 8 bolts. So the first calculation I'm not going to do on paper. I'll do it in this slide because it's pretty simple. We've got a 6-inch diameter seal, we'll assume, and 2,000 psi within that. So we need to calculate what is 2,000 psi multiplied by the area of a circle that's a 6-inch diameter. Calculate that area of that 6-inch diameter circle, and we calculate the total tensile load in the joint due to the pressure. That's the pressure times the area. That's 56.5 kips. So what's the external tensile load per bolt? P. It's not the additional tension in the bolt due to P, it's just the tensile load per bolt. So we take the total and we divide it by the number of bolts, assuming they get it equally. So 56.5 kips divided by 8 bolts is 7,000 pounds. What if we wanted to know what the additional tension in each bolt is due to the external load PB? It's not just 7,000 pounds, it's going to be a fraction of it, and we do not have enough information from that. We need some more. We need to know the relative stiffnesses of the bolt and the members. So here's how we determine PB. We need to know C. It is called the joint stiffness coefficient. P subscript B, the additional tension due to the external load, is C, the stiffness constant, times the external load. But what's C? Well, C depends on the stiffnesses. It's given by the ratio of the stiffness of the bolt relative to the combined stiffness of the bolt and the member, the sum of those two. Okay, so same slide as last time, except now we are given the stiffness of the bolt and the stiffness of the member. Stiffness of the bolt is 3,000 kips per inch. It would take 3,000 kips in order to make the bolt stretch a full inch, and it would take 12,000 kips to make the members compress by an inch. And we want to know what's the additional tension in each bolt that's due to the external load. What is PB? And we also want to know, assuming the bolts are unplated, unlubricated, and are preloaded for a non-permanent connection, what torque is required to achieve the proper preload, and what is the total bolt tension when the load due to the 2,000 psi pressure is applied. What is the total tension in the bolts? So let's do that first part. So we saw on the slides that PB, the additional tension of the bolt due to the external load, is C, the joint stiffness coefficient, times P, the load per bolt, the external load per bolt. What is C? C, we saw on the slides, is KB, the stiffness of the bolt, over KB plus K sub M, stiffness of the members. And we've got those numbers right here. So 3,000 over 3,000 plus 12,000. That's 15,000 on the bottom. This is just 1/5, 0.2. And I chose these numbers to be nice, but that is a very reasonable stiffness coefficient. These are approximately correct for a bolt if you make certain assumptions about how long it is. We'll learn how to calculate those soon. Okay, so let's calculate this out. 0.2 times 70/70 is 1414. Okay, and that's our answer. That is the additional tension in the bolt due to the external tensile load. It's not 7,000, it's a small fraction of that, 1,400. So we're going to assume that the bolts are unplated, unlubricated, and are preloaded for a non-permanent connection. If they're unplated, that means that our K factor that relates torque and load, so I guess let's remember that T is equal to K times Fi, the desired preload, times the major diameter of the bolt. And this K here is 0.3 in our case, because it's unplated and unlubricated. So we've got 0.3 times, what's Fi? What's the recommended preload? It says it's a non-permanent connection. So in that table it said 75% of the proof strength is the appropriate preload. What's the proof strength? Proof strength is, I should say proof load. What is the proof load? It is the proof strength, SP, times the tensile stress area, AT. And where do we get these? These are in the book. So let's look up the tensile stress area for a 5/8-18 bolt. So 5/8 is the major diameter, 18 is the fine thread, 0.256 inches squared is the tensile stress area. And what's the proof strength of this material? It's SAE grade 2. SAE grade 2, up to 3/4 inches major diameter. Minimum proof strength is 55 KSI. All right, let's multiply those out. 14,000 pounds is the proof strength. 75% of that. The recommended preload is 10,000 pounds. And plugging that into our formula for the torque as a function of the desired preload is 1,980 inch-pounds. And what's the total bolt tension when this bolt is under load? Well, the total bolt tension is the force in the bolt is equal to the preload, F sub I plus C times the external load. F sub I is 10,560. C is 0.2, as we determined above, based on the stiffnesses, and P was 70/70. Oh, but we actually already calculated that product. 0.2 times 70/70, this here, is just 1,414. And so the sum of those two, total tension of the bolt is 11,974. And notice that that is, even though we're applying 7,000 pounds, and we've got a preload of 10,000 pounds, we only go up to a total tension of the bolt of 11,974 pounds. So we are less than the proof strength of the bolt, despite the fact that 10,000 plus 7,000 is well over the proof strength of the bolt. So preload's good for a lot of reasons, and it doesn't hurt your capacity to handle external load. Takes a little bit more effort to do calculations with bolts, but it's worth the effort.